Hi, I am Vishnu from Pratisha Engineering College, and this is my embedded system internship project, the EV ADAS dashboard. So, the project stimulates an EV dashboard that monitors speed, battery state of charge, monitor torque and temperature, while also implementing ADAS features like forward collision, warning, blind spot detection, and fault alerts. So I developed firmware in STM32 Cube IDE using C, stimulated the STM32 F10 3C86 blue pill in PicSimLab and built a live dashboard in Python using Matplotlib. So the system uses ADC timers, USAT communication to process sensor data and transmit real-time telemetry. So now let me show you the system architecture. So this is my EV ADAS dashboard project built using STM32 Blue Pill, PicSimLab, and a Python dashboard. So the problem, so why smart EV dashboards matter? So modern EVs that generates a huge amount of sensor data and without a centralized dashboard, engineers can't monitor performance and safety at the same time, right? For that only data flows from stimulated sensors through STM32 ADC and control logic out over UART and into a live Python dashboard. So now let's see the real industry versus our projects. Okay. So each part of my simulation stands in for a real EV component. For example, um, PicSimLab's potentiometers that replace actual pressure and speed sensor, and UART that replaces a CAN bus. So now let's see the 9 phases of our project development. So I broke the project into 9 phases from environment step up all the way to the final live dashboard. Okay, so environment setup and GPI work peripherals. Okay, so first I installed the required tools and configured GPIO timers and USART for the firmware. So next this EV dynamics ADC sensor system plus EV dynamics model. So next I set up ADC channels to read accelerators, brake and temperature and build the EV dynamics model that can calculate speed, torque and battery drain. Okay. Next, also I have added like collision warning, blind spot detection, and time to collision, all driven by stimulated ultrasonic sensor. Okay. So next, I also implemented fault detection and alarm priority. Okay. Why I built a fault system means it is a bit field register and a 4-level alarm system from normal all the way up to critical. Okay. Okay, let's see our project workflow. So this is the diagram that shows complete 14-step data journey from reading the ADC to all the way to understand the dashboard display like alarms. And this is the fault diagnosis. And this is the interactive Python interface where the performance of the dashboard can be seen through graph, and this is the real pipeline from inputs to final display at the Python dashboard. Thank you. Okay, now let's see how the code runs. Okay, So here I have added the code in main.c. So let's check whether this has a error or not. Okay, let me walk you through this code that you can see oscillators, initializes CPU, and so now let me run the code. See, you can see here the build has been finished and there is no errors. Okay, so now I will open PicSimLab, and this is the component I used here. So while stimulating this board, which is also known as the blue pill, a low-cost ARM Cortex M3 is development board. So I chose this because it has enough ADC channels, timers, and GPIO pins to handle all of my EV and ADAS logic. Okay, and it's widely used in embedded prototyping. So it's a realistic choice for this kind of project. On the board itself you can see that the microcontroller, so the reset and boot buttons, and status LEDs for power and active monitoring. So this mirrors exactly what a real blue pill board looks like, right? So let me show you the spare parts. Okay, see, these are all the spare parts which I have pulled. Okay, since I don't have physical sensor, right? So PicSimLab that gives me the spare parts panel, so which acts as a virtual board. Here I have three slides labeled PAO, PA1, PA2. So these stimulates potentiometer for the accelerator pedal, brake, and monitor temperature sensor. Okay, moving these sliders, which is exactly like turning a physical potentiometer knob. Okay. Okay, then next to them there are ultrasonic sensors, right, which can stimulate front, left, and right, each with a slider that represent the distance to an obstacle in centimeters. Okay, so these feed my forward collision warning and blind spot detection logic. So at the end I have four LEDs wired to PB8 through PB11, representing my collision alarm and left blind spot, right blind spot, and fault indicator. These physically light up then the firmware detects a dangerous collision. Okay, so now let me show the project demo with you so that I will load the bin file of this project. Also, I have connected it to Python. Fine. Now the bin file is loaded in this microcontroller board. As you can see that The board is running. Now let me show you the Python dashboard. And this is our Python dashboard. We have speedometer, battery, and speed history where it will be shown as graph, and also we have torque, accelerator, brake, motor, alarm, fault, and these are all vehicles, and the distance will be calculated here. So now let me accelerate the components. So these are all spare parts, right? So if I run this, there should be change in the Python dashboard, right? So now let me increase the ultrasonic sensor. As you can see here in Python dashboard, it gradually changes, right? And also I can show you the accelerator, increasing accelerator. Now you can see the accelerator is increasing, right? Okay. Now when I apply the brake, so now when I apply the brake, this will be decreased. The acceleration will be decreased, as you can see. See, it is decreasing from 62 onwards, decreasing one by one. And also, let me increase, while increasing the front of the ultrasonic, so the alarm shows that it is critical since in the distance of 94 centimeter itself, right? And you can also see the torque, accelerator, and brake, and motor temperature, alarm, and fault, right? So that covers the full EV dashboard simulation from firmware running inside PicSimLab through UART telemetry to a live Python visualization. So this demonstrates real-time EV dynamics modeling alongside ADAS safety features like collision warning, blind spot detection, and fault handling, all validated without needing physical hardware. Okay, thanks for watching.